later what optimal transport has to do with this digging soil. So we know that everywhere in science, we encounter data that can be seen as some sort of distribution, either continuous or discrete. For example, here are some of the images of the normal and cancerous liver cells. And here is a grayscale facial images, and these are some galaxy images. We can view all these images as discrete distributions with the intensity of the pixel suggesting how much mass is located at the particular location of this pixel. So in this talk, I will use mass in a very loose term. Basically, it just means the amount of stuff at a certain location. And here is another physics example that we'll consider later. So this is a jet image in the pseudo-rapidity and azimuthal angle plane. And here mass refers to the transverse momentum of each particle at each location. I will explain that later. So one common features of all this distribution is that they all contain rich substructures that may tell us more about what the data it is. For example, in the facial image case, the substructure can be face, and the smiling face suggests a happy face. So given such distributions, there are several natural questions to ask. The first one is how to define a distance between two distributions that can make the best use of this rich substructure encoded. And related to that, how can we deform one distribution to make it look like the other? So just to clarify what I mean by these two questions, here you see a cow, and the cow is gradually transformed into a duck and into a donut. So when you define a distance, intuitively, this cow and this cow-ish thing should have a smaller distance than this cow and this donut, right? So this is pretty intuitive. And that is what I mean by the first question of defining a reasonable distance. And also we see the optimal way to transform this cow into a duck. And that is what I mean by the second question. And optimal transport is a mathematical theory that answers both of the questions. So at this stage, you may wonder why optimal transport? Why can't we just use the normal Euclidean distance? What's wrong with that? Okay, so let's consider a very simple example. Here are two dots, the blue one and the red one, and both have unit mass. So we can represent them as vectors in Rn, where all the entries are 0 except the ones that correspond to the location of this dot, right? So these are the two vectors corresponding to these two dots. So if we compute the normal Euclidean distance, then the distance between these two dots will always be square root of 2, no matter how far apart these two dots are separated. And this is not what we really want. What we want is a distance that can reflect the geometry of this underlying space, which we call the ground space. And now if we define the optimal transport distance in analogy to the physics concept of work, then in this case, the distance between the two dots will be square root of 13. And it will depend on the separation of the two dots. So you see that if the relative distributions of these pixels carry some physical meaning, then we cannot use a simple Euclidean distance, but we need to really resort to OT distances. So there are indeed many different types of optimal transport distances. One simple example is called the Earth movers distance, EMD. So for example, I have two distributions, E and E tilde. EMD is defined to be the minimum cost of turning E into E tilde, where cost is assumed to be the amount of mass moved times the distance by which it is moved. So this is the amount of mass moved, and this is the distance. So on the right, you see a nice visualization of how to transform E into E tilde. For example, look at this bright green amount of mass here. So this is transformed to here. And the optimal way to transform one distribution to another is called an optimal plane. Okay, so hopefully from this simple example, you now have some intuitive understanding of what optimal transport is doing. So before we dive into the mathematical details, so I like to emphasize here what our physics goals are, just to make sure we don't get lost. So here are the two physics scenarios we'll consider later. In the collider physics case, the distribution we'll study is a jet. And the goal is to explore the space of the collider events and find a better way to examine the LHC events. In the dark matter study, the distribution of interest is a satellite galaxy in a dark matter host halo. And our aim is to infer the dark matter properties via a principled comparison between simulation and observation. So I will explain the physics background later. So please just keep in mind our physics motivations. Okay, any clarifying questions before we move on? Nope? Okay, great. Nice. So let's dive into the math. So what you see here is two different ways to transform the image of the two founders of the field into each other. So the top and bottom rows are different ways to transform them. And Monge, so this older person, well, I mean, he's from further back in the history. So he is a French mathematician in the 18th century. So Monge actually started the whole field of optimal transport from a very simple and practical question. It was during the French Revolution, and as a military engineer, Monge was concerned about the question of how to build an earthwork with the least amount of effort. So in other words, how to rearrange a pile of dirt to look like another pile of dirt with the least amount of work. So this defines the fundamental question of optimal transport. So very surprisingly, such a simple sounding question turned out to be very hard and took well over 100 years to be formulated in a mathematically rigorous way. So that's a simple question too, and it took many, many years to be formulated exactly in a mathematical way. So it was not until the mid-20th century when the Soviet mathematician Kantorovich, this guy here, and he gave the problem a precise formulation and really kickstarted the whole field. And since then, many Fields medals have been given to mathematicians working on this problem. And recent years have really witnessed a surge of new interest in optimal transport thanks to its connection to machine learning. So the field of optimal transport is, of course, very vast, but for our own purpose, we will just break it down into two categories: the balanced optimal transport and its generalization to unbalanced case. So balanced optimal transport requires that the two distributions have equal total mass. So in the case of EMD, the definition is given here. So say we have two events, E and E prime, each composed of a bunch of particles, such as the blue dots here, and the total amount of mass of E and E prime is the same, so like here. And Fij is amount of mass moved from particle I in event E to particle J in event E prime. And theta ij is a ground metric between particle I and j, such as the Euclidean distance we used before. And furthermore, we need to satisfy this condition here. For the simple case presented, gamma is a conditions, is this set of conditions. So for this simple case, I can spell out precisely what this condition is. So for example, you have F11 plus F12 is equal to E1, which is the total amount of mass inside this particle. So basically, you can't move more than what is already there, and also you can't move more mass or less mass into a place where there's already a certain amount of mass.
So is there minimum amount? I mean, are they then should be discrete value of?
So it depends. So right now there's no minimum amount. So it's not a discrete amount of mass you move. Yes. Okay, good. So it's actually quite straightforward to generalize the EMD case to what is called the P-Wasserstein metric and WP. So here is a definition. And we can see when P is equal to 1, we come back to our Earth mover's distance. And when P is equal to 2, we have a distance called the Monge-Kantorovich distance, also called the 2-Wasserstein distance, W2. So in our work, we will focus solely on W2 distance. And the reason is because among all possible P, only the W2 distance enjoys a weak Riemannian structure, making it possible to linearize this metric. And we will see later that the linearization is a key that will save our life. So there are indeed two equivalent formulations of the W2 distance. The one we are familiar with is a static formulation, circled in purple. But it can also be caught in a dynamic form, and the formulation is analogous to the fluid dynamics. So if we think of rho as a charge density, omega as a current density, then this equation is nothing but the charge conservation law. And the W2 distance can be obtained from rho and omega by minimizing this cost functional J here. So let's work out a simple example. Suppose we have two Dirac masses at x0 and x1, again, both with unit mass. And using the static formulation, we can see easily that the W2 distance between the two dots is given here.
So by Dirac mass, you mean it's like a delta function?
Yes, delta function, correct. So let's define capital X as the line between x0 and x1, moving at constant speed, parameterized by this time parameter t. And then rho is a Dirac mass traveling at constant speed along this straight line, and omega gives this constant speed at time t. So therefore, the Dirac to Dirac geodesics in the W2 consists of a single Dirac traveling along this line, capital X. So up until now, we have only considered the case where the total mass of the two distributions are equal. And also mass can only be transported from one place to another. This belongs to the realm of the balanced optimal transport. Indeed, we can relax one or both of the conditions. So in addition to mass transportation, we can also allow mass to be created and destroyed. By doing so, we no longer need to strictly enforce the equal total mass condition. So this gives us an unbalanced optimal transport. So for example, if we only allow mass transportation, then we have to move this amount of blue mass all the way down here to the red bump here. However, if we allow mass to be created and destroyed, then we can simply destroy this amount of blue mass here and create this amount of red mass here. So this might give us a better notion of distance between the two distributions, because after all, intuitively, they're not very far apart, right? Okay, so I like to repeat one point here because it might be a little bit confusing. So while balanced optimal transport strictly requires the two distributions to have equal total amount of mass, unbalanced optimal transport can be applied whether the total mass is equal or not. So when the total mass is not equal, unbalanced OT still generalizes balanced OT by allowing mass to be created and destroyed locally.
Yeah, when you say optimal transport, what is being optimized?
Oh, the total cost. So cost defined by, so here, for example, cost is defined by J. So different types of optimal transport define the cost differently. So right now we are only considering the W2 distance. So this is the definition for the cost functional.
Yeah, but those are single. What's the physics behind it?
Maybe if you get a recommend distance.
Yeah. So think of the physics concept of work. So the total amount of mass moved times the distance by which it is moved. So you want to minimize this. For example, that is almost exactly the same as work, right? In the physics sense. Great. Okay, so this is a very nice visualization of different ways to transform two circles into each other. So basically, these two circles are exactly the same, except they are being located at different locations. So on the first line, you only have mass creation and destruction, and no mass transportation is allowed. So what you do is you simply fade out this top circle and fade in this bottom circle. And in the bottom line here, only mass transportation is allowed. There's no mass creation and destruction. So what you do is just you move this circle downwards. So already here, you can glimpse at a parameter that controls how much you are allowed to transport mass and how much you're allowed to create and destroy mass. So it will be a critical parameter for unbalanced optimal transport, which I will discuss later. So first, let's pause here and step back for a moment. So before introducing unbalanced optimal transport, how did we deal with a situation where the two distributions have unequal total amount of mass? So one simple way is to always first normalize your distribution so that they have total equal amount of mass, and you then use the standard balanced optimal transport. However, by doing so, you may lose some critical information encoded in the total mass difference, right? So another way is to add a term directly to the balanced optimal transport distance, such as this, to account for the total mass difference. So for example, for the EMD distance, we can add a term like this. And this is what was done in the original paper introducing EMD to collider physics by Jesse Taylor and his group at MIT. So however, this additional term might really screw up the nice properties of the EMD metric, and it is really rather ad hoc. It is not clear what relative weight you want to put in front of the standard EMD piece and in front of this actual total mass difference piece. So this is why we need to introduce unbalanced optimal transport. And this is what we considered in our own study. Okay, great. So now there are also many types of different distances for unbalanced optimal transport. We'll focus on a particular, so it's somehow being cut here, but we'll focus on a particular distance called Hellinger-Kantorovich distance, shorthanded as the HK distance. So again, there are two formulations for the HK distances, the static one and the dynamic one. I want to point out the dynamic one because it's very analogous to the W2 definition. Here we have the continuation equation with source. So this additional zeta term accounts for the mass creation and destruction. So what is nice about this HK distance is that just like its balanced twin, it also enjoys a weak remaining structure and can be linearized in a similar way as W2. So again, let's work out a simple example and consider the previous direct mass case. So this time they have different total mass. You can see they have different sizes here. And the HK distance between them after some math is given by this. So again, rho gives you the mass density at each time instant t. Omega gives you the speed at time instant t. And this actual zeta terms tells you how much you create or destroy mass at this particular time instant. There is one complication here that is new to the HK distance. So if the distance between the two Dirac masses in this ground space is smaller or equal to pi over 2, then the HK distance between them is given by this vector here, the length of this vector here. However, if their distance in the ground space is larger than pi over 2, then you simply don't move any mass. You just destroy the mass at the blue dot here and create the mass at the red dot here. So in other words, there is an intrinsic length scale in the definition of the HK distances. So let's take a closer look. So here is a complete general definition for the cost functional we want to minimize for the HK distances. So note that the length scale kappa circled in pink. In the previous slide, we set the kappa equal to 1/4 for simplicity. So this length scale kappa, actual parameter kappa, controls the relative importance of the transport part of the cost and the creation and destruction part. So when kappa goes,
the integration variable?
It is this row. Okay, great. So
Sorry, now I'm confused though. So your J on the left-hand side depends on rho, but rho is an integration variable on the right-hand side. So the right-hand side does not depend on rho.
So actually, I think so your question is on the right-hand side, you have the dependent, you integrate rho out, and on the, so this, how to say that? So this is actually an implicit dependence on the time parameter t, and what you really integrate out is time parameter t. Okay, good. So when kappa goes to infinity, then we can't have any creation and destruction part because then this part will be an infinite cost. So you don't have any creation and destruction part. That is when you recover the W2 distance. So showing here. And when kappa goes to 0, then the cost of creating and destroying mass is basically just 0. So you don't move any mass, you just create and destroy mass. So in the simple case of the discrete distribution, this gives you the ordinary Euclidean distance. So for example, here you just create all the blue dots here and destroy all the blue dots here and create the green dot here. Okay, good. So one more thing to mention for the HK distance. So that is a normalization of mass. It turns out that actually the HK distance between two unnormalized distribution can indeed be recovered from the HK distance between the normalized distributions. So what this tells us is that the unbalanced effects of the HK distance are actually already fully encoded in its behavior unbalanced on the normalized distributions. So therefore, the benefit of using the HK instead of W2 lies not really in its ability to deal with total mass differences, but in its ability to deal with local mass discrepancy. So this point is actually pretty important because it shows us that the naive way of incorporating the total mass difference is actually not going to work, because it's not the total mass difference that is important. We really need to use the full machinery of unbalanced optimal transport to account for global and local mass discrepancies. So we have now covered most of the basic concept of optimal transport metrics. Can we apply them to the physics user cases? Well, there is one obstacle, and there's always one obstacle. So the obstacle is this. The OT metrics turn out to be actually pretty expensive to calculate. So how expensive? It takes 100 more times to compute than the normal Euclidean distance, which only needs milliseconds. And to compute the entire pairwise distance for a data set with n samples, we will need OT computation on the order of n squared. So usually for a practical data set, n is on the order of 10 to the 5th or even more. This means that it will take more than 16 years on your desktop to compute OT distance matrix for even a very normal data set. So this is obviously not acceptable. So we are really in bad need of a method to speed up the OT computation. And here enters our superhero, the linearized optimal transport. And this is actually one of the main contributions of our work.
So the problem is analogous to like the path of least action, but not having the Euler-Lagrange equation. You have to sample every single path.
Yes, kind of, yes. Okay, so our goal is to reduce the computation of OT distance and maybe use the Euclidean distance instead. So the essential idea of linearized OT is to project everything onto this tangent plates at a particular chosen reference. And then we can do all the calculations on this tangent plane, which nicely turns the OT computation to the Euclidean distance. So because now we only need to compute the OT distance between the reference to each of the data points, instead of between the data pair of data, we also have successfully reduced the OT computation from n squared to n. And as a benchmark, to compute the LOT distance for more than 100,000 data points on an iMac takes only 10 minutes, whereas the task is infeasible even if we move to our UCSB cluster, which is not so fancy, by the way. Okay. So there's an additional advantage of using this linearized framework. So now instead of storing the whole entire distance matrix, we can actually just record the linear embedding for each data point, which we call the LOT coordinates. So, and the distance computation can be pushed downwards to whatever models we are using, because now the distance is just a normal Euclidean distance. So this is pretty amazing, right? Sadly, this is only available for W2 and HK distances, and that is why we focus on these two distances. Okay, question.
So you can see that the Euclidean distance is not correct, or like not the correct distance to use, but why are we using it now?
Oh, so I got the same question from my another audience. So basically, right now, we are in the OT space, kind of. So basically, what you are doing is you project all these points onto the tangent plane at the reference sigma. And this tangent plane is no longer the previous ground space. So previously, when we are calculating the Euclidean distance, we calculate the Euclidean distance on the ground space. So now this is in the OT space. So it's a different space.
Is that like locally Euclidean as opposed to globally Euclidean?
It's not even that, because now we are in a completely different space. So previously we are in some ground space you choose, and now we have already in the OT space. Great. Any other question?
So can you translate back to the previous state? Is that does it have memory? I mean,
what does it have? What?
Say, for example, you calculate the distance. So I don't have intuition about the data you say, okay, but I'm wanting the geometry you have, okay. So in the Euclidean space, the space that you created, so the distance between two, so you create, let's say that you have a distance between 2 points. So can you translate back to the original space?
The ground space?
Yeah.
Nope, it's not that simple. No. I would like to know how to translate that into the original space, but I don't think that it's that simple. Yes. Okay. So I will show you how to do the linearization in detail here. So say I have a reference R, and it consists of a bunch of black dots. And we first compute the optimal transport plan between this reference and say a particular blue event. And the Rij is the amount of mass you move from the ith particle in the reference to the jth particle in the blue event. And the barycenter is just a weighted average of the location where the ith particle is sent to. So once we have this barycenters, this one, the Z, we can calculate the LOT distance between the blue event and the green event by this, which is, as you see, is nothing but a weighted Euclidean distance. So it is actually theoretically guaranteed that our LOT distance converges to a true metric when the reference is continuous. In practice, we do find that the LOT distance is a fairly good approximation of its exact counterpart. The error is typically within 5%. But I do recommend double checking on this using a small data set when you are playing with linearized optimal transport. So again, let's walk through a simple example. So the upper two plots show how to transform the mass in the green reference to the two distributions separately, respectively. And the lower plot gives you the LOT distance and the corresponding LOT transport plan between the blue distribution and the red distribution. So here you can see the LOT distance is 1.07, whereas the exact OT distance between the blue and the red distribution is 1.06. So they are quite close. That's good.
Wait, sorry, how are the top and the bottom related?
Okay, so the top is the exact OT distance transformation from the green dots to the blue dots and from the green dots to the red dots. And to get from these two plots, you can get this by subtracting at each point the vectors. So for example, at this point, the vector is from this to here, and this point is also this to here. And when you subtract them, you get 0. So basically, you do the vector subtraction at each point, and that gives you the LOT transport plan between the blue dots to the red dots.
I see.
Okay, that makes sense?
So the green dots are the intermediate stuff.
Yes, that's a reference I choose. Okay, great. Okay, nice. So the above linearization is for the W2 distance. To linearize the HK distances, the ideas are basically the same, but the math is more involved. So basically, the tangent space now consists not only a vector field V, but also a mass growth field alpha. And if you are so mathematically inclined, please read our second papers for more details. And I will send the slides to Flip later. Okay, great. So now we have covered balanced and unbalanced optimal transport, and we have seen how to linearize two special OT distances, W2 and HK. We can now apply the machinery we developed to collider physics. So any other questions before we move on this math part? Any other question?
Sorry, when you're picking the reference, is there a best way to pick that, or?
Yes, that's a very good question. So remember here, I showed you that in the continuous limit, this distance is actually a real metric. So it is reasonable to pick this reference that is distributed kind of uniformly evenly on your ground space. So don't pick a reference that is only like direct mass. So that is not going to be a good reference. But we have also experimented with different variety of references, and it's not going to give you much different results as long as your reference is reasonable.
Yeah.
Okay. Thanks.
This is analogous to picking a Bayesian prior. In some sense.
In some sense, maybe yes. Yeah, but it's really stemming from this theorem. I think this one is proved in our first paper.
So is the reason why the linearization is such powerful? Is the reason that we can reduce everything to matrix multiplication?
So I would say the reason is because for the W2 and the HK distances, they have the Riemannian structure. So that is what allows you to do the linearization, to put a tangent space. So that is what makes a tangent space legitimate. And if you think if this manifold is like very rough, then there's no reason why you can put on a tangent space on it, right? So to make this whole system work, you really need a somehow smooth manifold where you can put where you pick a reasonable reference, and then you can do everything on the tangent space. Okay, nice. So now we'll move into physics. Yeah. Okay, so let me first just introduce some physics background for people here who might not be within the Collider community. I don't know, maybe everybody here is a Collider community, so I'm just, yes. So here is a cartoon for what we think is happening when two protons hit each other in the LHC. So presumably some new particles are being produced in the collision, which then decays into daughter particles and then undergo hydrogenization. At the end of the day, what we collect are a bunch of energy deposits on our calorimeter cells. So we can therefore represent each collision event as an energy flow on the calorimeters like this. So for example, we see an event display for TT bar event where each top quark subsequently decay into a three-prong jets, shown as higher energy deposits here, one jet, another jet. So these jets, which are just collimated sprays of final state particles, they are a very good phenomenological tool for us to study the underlying hard collisions because jets originating from different hard processes tend to exhibit different distinct substructures. So for example, jets from the hadronic decay of a boosted heavy particle tend to have richer substructures than jets coming from a QSD background. So jet tagging is a pretty important task. So traditionally, what we do is we design handpick substructure observables to study jets, such as the famous N-subjectiveness. So with machine learning, more and more works now turn to this powerful set of tools for a more data-driven complementary approach. So in the language of machine learning, jet tagging is just a classification task. So here I listed a few machine learning-based approaches for jet tagging. All these approaches need to first cast the jets into a suitable representations. For example, cast them as images for convolutional neural network and as sequences for models inspired by natural language processing. A common drawback for this all-in-one machine learning method is that it's relatively hard to look inside the black box to understand what is being learned. So it would be nice if we can represent jets not as some general images or sequences, but in a physically more meaningful way. So this is where optimal transport comes into the picture. So let's first understand why optimal transport is even suitable in this case. Presented in the Wi-Fi plane, a jet is nothing but a collection of particles, right? Which can be naturally viewed as a discrete distribution. So here, mass is chosen to be the transverse momentum of each particle. I like to emphasize that the choice of this ground space and the mass is purely problem specific. And indeed, it encodes the essential physics that we input into the problem. So here for the jets, we choose the ground space to be the Wi-Fi plane, the ground metric to be the Euclidean distance on this plane, taking care of the periodicity on the phi axis. And we choose the mass to be the particle PT. Other choices, of course, exist and should be and will be studied in the future. So we see jets are discrete distributions with rich substructures, and the relative locations of their constituent particles carry important physical meaning. If we want to define a distance between two such jets, the optimal transport is a natural way to go. For example, here you see the transport plane and the W2 distance between two QCD jets. So, but why do we need a metric in the first place? Well, if we just consider the task of jet tagging, we intuitively want jet sets coming from different underlying collisions to be far apart, whereas jets coming from the same type of process to be close to each other, right? And if we can endorse the space of Collider events with such a metric, then classifying jets will be easily achievable even with simple off-the-shelf machine learning models. So it turns out that actually equipping the Collider space with such OT distances not only accomplishes this practical task, but it also provides a very surprising unified framework for various phenomenological tools studied in jet physics. So let's uncover the magic now. So the work presented here was done by Jesse Taylor's group at MIT. So what they showed is that many concepts such as IRC safety, event observables, jet algorithm, pile-up mitigation, they can all be unified naturally in the geometric framework of optimal transport. We can even define a theory space and compute the precise distance between different theories. So let's zoom in on a particular jet observable and subjectiveness. So this is a normal definition for the n subjectiveness. And the OT formulation suggests that the n subjectiveness can be understood as the EMD distance between the jet and the manifold of all n particle jets. So the ratio tau n versus tau n minus 1 is then the relative distance between the manifold Pn and Pn minus 1. So this is very powerful.
These are like orthogonal distances, or there's some reference
This is the EMD distance.
to what? I mean, is there some reference to jet?
So, okay, that's a very interesting question, and I wish to explore this further, but I know Jesse's group, they are actually actively working on this problem right now. So what they've been doing is, instead of say I fix a manifold and pick the distance between the particular jet and the manifold, I actually tune the two dots in the manifold and then say, okay, for this particular configuration, it gives me the minimum distance. So that's how they implement this. But there are certain problems associated with that, but we can talk about that later. Okay, good. So now let's take a look at what OT can offer for jet tagging. So in our work, the task considered is to distinguish QCD background jets versus boosted W boson signal jets. So all jets are simulated via the standard pipeline, and they are clustered with a wide radius R equal to 1 to capture all the decay products of the boosted W jets. So the transverse momentum of the jets are either between 500 to 550 GeV, sorry, or within a wider range, 500 to 1500 GeV. So we pre-process the jets to make sure they are centered and aligned so that the OT distance calculated will not depend on any artificial differences in the data, such as rotation or translation. The distance we examined includes a linearized W2 distance, which is represented as kappa goes to infinity here, and the HK distances where we tune the kappa value, the hyperparameter kappa, to study its effect on tagging performance. So the performance is summarized in a single number called AUC. Basically, when AUC is equal to 1, it means you have a perfect classifier. When AUC is going to around 0.5, it means you just have a random classifier, which is bad. So the actual procedure for the linearized OT framework goes as follows. So given a set of pre-processed jets, we first fix a reference jet, which for us is just a uniform distribution on the Wi-Fi plane. We then compute the LOT coordinates for each of the jet with respect to that reference. And finally, we feed the LOT coordinates into a classifier such as k-nearest neighbor in the first row and support vector machine, SVM, on the second row. So they are very simple machine learning models, and we understand the math and what they are doing actually. And this outputs the final AUC values. So as a benchmark, we also compute the AUC for the original EMD approach by Jesse's group and the traditional observable and subjectiveness. So I want to make 3 observations here. First, our linearized framework achieves tagging performance comparable or even better than the EMD approach with significantly less computational power. Indeed, to compute the LOT coordinates on 200,000 jets only takes less than an hour, whereas it is infeasible to calculate using the exact EMD metric. And that is why we don't have the 2 lines here in this plot. Second, when the PT difference is large, focusing on these 2 columns, the unbalanced HK distance actually shows a clear advantage over the balanced W2 case. And third, most importantly, there exists an optimal value of kappa for which the tagging performance is the best. And this optimal kappa is on the same order of magnitude as the typical length scale present in your data. So in our case, it is a typical separation between particles in a jet. So we have also performed many other studies using the linearized OT framework, such as its sensitivity to pilot contamination. And if you're interested, you can just check out our papers here. So, yes, question.
On this slide, you show jets at different energies. However, assuming they come from the same type, for example, on the top part, okay? How could you use optimal transport to classify?
Oh, okay. So first of all, there's no top clock here. So the task is to distinguish QCD.
It's assumption. So I mean,
Mm.
apparently for a very high energy jet and for a jet which just above the mass threshold, they look very different from the perspective of a detector,
Mhm.
but they still have the same physical region.
Yes. Mhm.
But I guess your target is to distinguish jets of different types.
Yes,
So-
from different origins.
So
Yes,
how
correct.
do you use your algorithm adaptively to the change of energy jet PD.
Okay, jet PT. So if you have a wider jet PT, this is just in your cost it in the optimal transport language, it is a total mass difference. So basically, if your PT difference is large, it means one of your distribution have a small total mass, whereas the other distribution have a large total mass. So you, as you have seen, the HK distance already take care of that. So this is already incorporated into the HK distance framework. But for the W2 case, we normalize everything. So we normalize all the distributions to be total, same total amount of mass, which in this case is the same total PT for the jet. Mm-hmm. Yes.
How could you ensure during this renormalization? How could you ensure that the features you wanted to look at does not be it is not erased?
Yes. So that is when you look at the W2 classification result. So it's not as good as when you don't erase that information. So what is shown in these two plots is that if you do not erase that total mass difference information, and if you incorporate that in a good way, then it gives you a very good performance. So yes, the total mass difference is important in this case. And that is being incorporated in the dotted blue lines. Yes, sure, good questions. So I'm going to switch to a completely different physics topics. Is that okay? Good. So I now want to discuss the study of dark matter. So it is based on my current ongoing work in collaboration with Mary Angela and her grad student Dylan at Princeton. And our work is expected to be published late this fall, hopefully. So first to clarify, this beautiful picture here is not real, but it is an artist's imagination of the dark matter halo surrounding our Milky Way. So drawn in this mysterious purple. So this is quite lovely, right? And this is the topic of our current study. So we all know the existence of dark matter from its gravitational interaction with ordinary matter. So for example, look at the spiral galaxy here. If there were no dark matter, then the velocity of the stars further away from the galaxy center would be much slower than what is actually observed. So this theoretical rotational curve and the observational rotation curve indicate the existence of some new non-luminous matter. So there are, of course, many experiments trying to detect dark matter, either directly or indirectly. Most of these experiments depends on the assumption that dark matter also interacts with the ordinary matter in some other way besides gravity, for example, through weak interactions. Then these experiments search for signals of, for example, the decay of dark matter into ordinary matter. However, these are still conjectural. Up until now, the only 100% sure evidence is that dark matter participate in a gravitational interaction. So an alternative way to hunt for dark matter is to look closely at the sky and examine the galaxies. In particular, one promising probe is a dark matter halo. So the story goes as follows. The dark matter halo provides a gravitational potential that draws the luminous matters into its gravitational well, which gradually forms a galaxy. And as a natural law, large halos eat smaller halos. And so larger dark matter halos grows by absorbing nearby smaller halos, which then become bound in the large halo's potential well, and then become a subhalo. So in the plot here, this huge fuzzy purple cloud represents a large dark matter halo. And these smaller clouds circled here are the subhalos. So each subhalo hosts its own luminous stars, most likely some dwarf galaxies. So let's call them satellite galaxies. All these subplots show you subhalos with their own satellite galaxy. As you can see from the bottom row here, some of the subhalos may also display further substructures, which we call sub-subhalos. So since right now our observational precision is not yet that advanced, it may be hard to resolve such sub-subhalos. Therefore, for now, we just stop at the subhalo level and only concern ourselves with a halo composed of a few subhalos. So now we know dark matter halos have interesting substructures. Oh, this is cut. Okay, never mind. So the distribution of their subhalos carry important physical information about the property of the host halo. If somehow we can represent the dark matter halo as a discrete distribution in some sort of ground space, then we can use optimal transport to define a mathematically well-motivated distance between the dark matter halos, just as what we did in the jet physics case. So for example, in the two plots here, we see two simulated dark matter halo with roughly the same mass as our Milky Way. One subtlety here, because we cannot observe dark matter directly, what we see are their luminous counterparts. So in the case of the halo, it is a host galaxy, and in the case of the subhalo, it is a satellite galaxy. We can know the satellite galaxy.
Sorry, can I ask you? This is something I know. For the top panel, is that this is the abundance of satellite halos inside a host halo, is this right?
Yes, so these are, say, several satellite galaxies inside that host halo. And I'm not...
The galaxy or halo?
Galaxies, not halos.
In a simulated galaxy.
Yes, simulated galaxies. Yes, it's a luminous thing. So because at the end of the day, what we want to do is to compare the simulation with the observation. There's no, it doesn't really make sense to use a subhalo itself. So it really makes sense to use observable probes, such as a satellite galaxy.
So, okay, the x-axis is the distance.
I'm going to explain that.
Okay.
Yes, sorry. Yes, so so for the satellite galaxy, we can observe their properties through the telescope. So for example, we can observe the distance from the satellite galaxy to the center of the potential well of the host halo. So that is, roughly speaking, there's some normalization factor, but roughly this is the x-axis. And for the y-axis, what we want to do is you can measure the velocity of the satellite galaxy with respect when it is circling around the host halo, galaxy, and you want to measure the velocity there. So this is the y-axis. And right now, the size of the dots is a mass of the satellite galaxy on a log basis. So of course, you can use other properties such as luminosity and metallicity and any other properties that you can measure for the satellites. And we are actually using other properties in our actual work. And I just want to, before we go on, this is very preliminary work, so don't read too much into the results. So we are still refining our framework. Okay, good. So we have now successfully turned a dark matter halo into a discrete distribution through this process. And optimal transport gives both the distance and the matching between the two halos, such as shown in this plot here. So of course, you can again ask, why do we need a distance between halos in the first place? What I wish to argue through the case below is that distance is a very useful tool to have, and it can help us in many different settings. So just as a test case, our job now is to constrain the mass of the Milky Way dark matter halo. So the aim is to see whether our framework works. That is, whether using optimal transport as a distance between halos even makes sense. So the halo mass is a relatively straightforward parameter to tune in many of the simulations. So we pick this as our parameter instead of some of the subtle dark matter properties. So just to give you a head start, our ultimate goal is to be able to infer the particle nature of dark matter, for example, its self-interactions, which the halo distribution is particularly sensitive to. So again, our theory parameter is a mass of the dark matter halo of our Milky Way. So it turns out that this is quite an important question in its own right. People have done a lot of work to infer our Milky Way mass. And as of 2020, these are the values we got via different observational and statistical probes. Better constraining the Milky Way mass can help us understand why, for example, our galaxy holds fewer satellites than predicted by simulations. And this will in turn inform us on the nature of the problem challenging our lambda CDM model. So it is important to know our Milky Way mass, which will, by the way, determine the fate of the Milky Way and ourselves. Now let's see how our newly defined OT distance between halos can provide us with an alternative way to deal with this life and death question. So let me reformulate. The problem we face is that we have the observational Milky Way and a bunch of simulated Milky Way like halos. So from this, we wish to infer the actual Milky Way mass. This problem belongs to the statistical field of simulation-based inference, also called likelihood-free inference. These types of problems share the common feature that it is straightforward to go from the theory parameter to the simulations. So basically, this forward direction is easy in the sense that you just run your simulation and your software outputs some of the halos. But because the simulator is usually very complicated, involving lots of approximations and stochastic components, it is impossible to go from the inverse direction and to deduce a closed form solution for the likelihood function. That is to say, we need some special tricks to get the posterior distribution of the theory parameter from the simulation. So this type of problem occur actually everywhere in natural sciences, and there are a lot of current interest in using machine learning to tackle this problem. Most of the recent works are focused on constructing an approximate surrogate likelihood function using neural networks. But in our work, I focus on a different type of approach called approximate Bayesian computation, ABC, in order to utilize the OT distance defined between halos. So I also incorporate a new technique called active learning here to help us deal with expensive simulators. So let's take a brief detour. So I think I'm almost out of time, but I think 5 more minutes, I'm good. So let me just take a brief detour to approximate Bayesian computation. ABC is actually pretty straightforward. Basically, you pick a value for your theory parameter from some prior, and generate some simulated data from that value, and you compare your simulated data with the actual observational data. If they are close enough, according to some metric, you keep this simulation. If not, you throw it away. At the end of the day, the simulation you keep give you an approximate posterior distribution of the theory parameter. So you can see that key to this framework is a notion of similarity. That is a distance between simulation and observation. And this is exactly what optimal transport offers. And also, you can probably sense that this ABC framework is not going to be very efficient. Usually, it throws away way too many points and ends up requiring way too many simulations to give you even a reasonable posterior estimation. So, and we know that simulations are very expensive. So that is the reason why we also need to improve this statistical framework itself with the help of active learning. So here I show a schematic flowchart for the detailed statistical framework we used in our work. I don't think I have enough time to explain this in detail, but I'm happy to take any question or chat after the talk. So the essential idea is that you have your initial training data set, which is composed of a pair of your theory parameter, that is the dark matter halo mass, and the distance, that is the OT distance between your simulated halo and the observed Milky Way halo. You then get a regression relation between the halo mass and the OT distance. And finally, active learning tells you, based on the current data, what is the best point to simulate next for the theory parameters in order to minimize the total number of simulations. So this statistical framework was first developed in this 2015 paper, and the methodology was applied to a cosmological context in 2018, though none of the work used optimal transport to define a distance notion. For some reason, there aren't many follow-ups to these works. Probably people get too absorbed by the machine learning alternative approaches. But what I wish to convey is that this statistical framework is also potentially very powerful and worth our study. So in our case, this is just what we need to make the full use of OT distance. So to give you an idea of what I mean by active learning, here you see the OT distance versus a halo mass regression plots. And in this row, the black dots are your initial training data set. And this gives you an initial posterior distribution of the halo mass with a 95% credible interval. Then active learning tells you where to simulate next. So these red dots are the next location of the halo mass where you would run your simulator and generate your new simulated hosts. You add them to your training data set and enter the next round. When you decide to stop the loop, you have your final data set, which gives you the resulting posterior for the halo mass, showing here. And it says that the most probable Milky Way halo mass is 10 to the 12 point something 15 or something like that times the mass of the sun. So now, again, this is very preliminary study, so I wouldn't read too much into the result. So what I wish to point out is that our result is consistent with all the other previous results. Of course, it suggests that our framework is working and OT is pretty effective in capturing the differences between halos. So we will do more work in the future, in the next few months. And so please stay tuned for our future paper. So that concludes my 2 use cases of optimal transport in high energy physics. Let me summarize a few take-home messages. So of course, hopefully you now agree with me that optimal transport is great. And whenever you have 2 distributions whose substructure contain essential physics, you should consider using optimal transport to equip the space of your distributions with a metric. It will help you in many different settings. I've shown you its usages in jet tagging and the inference of the dark matter halo mass, but you can come up with your own creative applications. So I wish to point out that OT also proved useful in a more theoretical setting, such as a study in this recent very exciting paper. This is about the equivalence of the OT flow with exact renormalization group flow. So check this out if you are interested. So now just to give you some possible inspirations, I listed here some of my own future research directions. So on the framework development side, one thing I plan to do is to be able to incorporate different types of objects in the distributions. For example, instead of having a grayscale images, I want to have a colorful image. So in this case, there will be a certain additional cost associated with converting a blue pixel into a red pixel. This is called multi-species OT, and our math people are actively developing this framework now, and we wish to apply it to the collider physics case in next year. Okay, so we may also want to incorporate certain symmetries into the OT framework. For example, instead of pre-processing the jets to center and align them, it would be nice if the OT framework can automatically take care of this, so that in that way we can get rid of this ad hoc pre-processing step. Okay, and another thing at the back of my mind is how to incorporate uncertainty quantification into this OT framework. So to further our study of optimal transport for collider physics, what I wish to do in the near future is to use optimal transport to define an anomaly score. So here one needs to define a background manifold and use OT to calculate the distance from a certain event to this background manifold. So this is likely to be a good measure for how anomalous this event is. And in principle, we can also define a theory space and compare different theories with each other. So this really depends on how to pick a suitable ground space and a ground metric. And I do have some idea about that. I can chat about this later. So for the dark matter study, so right now we are still at the very beginning of our study, and there's a lot to explore. And one way is to think of other statistical frameworks to incorporate the optimal transport distance. Of course, our ultimate aim is to be able to infer some microscopic properties of the dark matter, and this is what we are going to do for our next step. So that's all from me. And again, thank you for listening to my long talk, and sorry for all the technical disruptions, but hopefully you at least learned something from my talk. Thank you.